I wanted to give you a little bit of heads up on what is this platform. This every one of you should be able to use in case you're not yet using it. This is called as Collaboratory from Google. Collaboratory is a cloud-based platform from Google, freely available to all deep learning developers who want to develop the custom models in deep learning, whether it is RNN, CNN, MLP, doesn't matter, whatever. But it offers GPU support out of the box from Google's perspective till a limit. If your problem is really large, they also have a paid collab version, which I think most of you will not need for the problems which you are going to work on. But it is impossible for some of these problems like this VGG based MNIST to generally work in your own laptop. I will anyway upload this workbook into the class portal. But what you can do is all of you with a Gmail account can go to collab.research.google.com. It opens up a thing like this. Then you can actually upload a notebook of yours, which is in your local directory, and go and get executed. So it's not that this is required to be shared as a URL from the Google Colab. So I want all of you to do this experiment of uploading this file and then executing it. Executing it is fairly simple. It collects each of these modules. Then you have to click on each of the cell to run it, just like Jupyter Notebook. There's very much Jupyter friendly research environment with GPUs at the back end. So let us look at this particular code base. Let's forget about all of this. These are the standard normalizations, etc. This is the load data, which is talking about downloading the MNIST data set. So what this is doing is this is downloading the MNIST data, which you know is the standard character recognition where the output class is a 10 class classification, where it is one of the 10 characters, 0, 1 to 9. Then what we do here is once we obtain our data, we have reshaped all the data into 28 by 28 pixel. Now comes the interesting part. So what we've done here is we have taken the explicit pre-trained model called as VGG16. VGG16, as I've already mentioned, is a pre-trained model with the corresponding neural network already serialized inside libraries like Keras, PyTorch, TensorFlow, etc. So we're creating the base model by importing VGG16 weights based on what has been developed using ImageNet based image data as the training data. And here is the important element, which is what we call as including top equal to false, because what we want to do here is, while the ImageNet classification may be about the top layer being able to give output for probability for all of the 1,000+ classes of images, in our case, we want to reuse all the layers except the top layer, which is going to be specific for us, which is the 10 class classification problem. So we explicitly say that extract all the layers of ImageNet, but please don't include the last layer of classification, which is the softmax layer, which we've seen in all the architectures, right? If you see all the architectures, the final layer is the softmax, which is corresponding to the exact number of classes for ImageNet or for MNIST, whichever class of classification you want to do. After the fully connected layer, you look at final layer will be the actual classification, which is the softmax. So here the top layer is removed, and the images in ImageNet are 32 by 32 images. So there is a bit of a challenge. What was the structure in MNIST? We were looking at 28 by 28 images. So what we've done here is we have loaded the ImageNet model from VGG16, which is the based on ImageNet data, the 16-layer VGG model, which we already looked at. It's a layer which is consisting of a set of convolutions and max pooling with RLW filters. Then finally you have a set of fully connected dense layers, ultimately leading to a dense softmax layer, which is going to be the classifier. So here we're using all the layers except the final classifier. So now that we need to look at input to this large network coming in form of 32 by 32 with RGB, what we do is we take the original data and write a pre-processing routine where we develop a resizing method for each of the input images, which are 28 by 28 with 3 to 32 by 32, so that they are made ready for inputting to our deep learning model. So finally, we are able to convert that in terms of converting the original images into 32 by 32 by 3. Now we are ready to reuse the machine learning neural network as obtained by the VGG16 model. Now, what you see here is the set of transformations after we got the final output layer before the sigma softmax layer, which we removed from the top layer. What we do is we take the output layer from the VGG16, we flatten it, then we add a ReLU function to each of them, then add a 200 layer fully connected 200 node dense layer, which is fully connected here. Then since our output is 10 class classification, the final output layer will be a softmax activation based fully connected network with 10 outputs as the output of the classification. So you can think of there are 16 layers in the VGG. Then we have added one dense layer of 200 with ReLU. Then we have added one dense layer with 10 as a softmax activation. So what we have done is we've taken 16 and then added 2 more layers. So our net result will be an 18-layer model. The final output, as you can see, is which takes at the start base model.input, which is the 32 by 32 by 3 as the image. Then output will be the one of the 10 classes which has to output as a class. So what we have done is we have created an 18-layer network by reusing 16 layers, and 2 layers we created our own. Actually no, 15 layers, because the last layer, softmax layer in the previous case, we have removed and added 2 layers. So it's become 17-layer model now, because as we remember, we had said that filter out the last layer in the base model, because our output is not based on ImageNet output, which is thousands of classes of images which you have to output in terms of softmax for the ImageNet classification problem. But we're not concerned about it. What we want to do is the collective knowledge of all that which is there in the 15 layers we accumulated till now. But to that we want to add specifically for our domain what kind of specific classification we need to do for our class of fonts. And that is what we're going to get here by, if you see the sequence, we have base model dot input given as the input. Finally, what we get is the dense 10 as the output, which is the 10 layer. So now we can visualize the network as it goes as input to the VGG net as the basic MNIST image transformed into 32 by 32 by 3, then goes through the 15 layers of VGG, then goes to the dense 200 layer ReLU, then goes to the final classifier of softmax, which is giving 10 classes as the output. So that becomes a 17 layer model as a final network for you. But out of that, how many layers did you program? You didn't program any of the 15 layers yourself. You used the AlexNet's 15 layer. So if you want to see the architecture, finally what it comes out, you can see that by model.summary. So you can see what we're doing here. We look at input layer, then there is a convolution layer, max pool layer, convolution layer, max pool layer, 3 convolution layers after that, then max pool layer, 3 convolution after that, then max pool, then 3 convolution, then max pool, then you flatten it out, then you add a 200 layer dense model fully connected, then we have a dense softmax output as our own custom layer. So last 3 layers are our own, whereas we have removed the final 1 layer from the previous and added these 3 layers. So now you have, as if you have created from your own hand such a large network. Suppose if you were to do this yourself, what would you have to do? You have to create a collection of convolution and max pooling as a set of architecture, and then train it on the input data of ImageNet, and then get all this data and then run it on your own ImageNet. Instead, what you're doing is you're taking an existing network and chipping off the top layer and adding a little bit of that. So here is where I would say the hyperparameter, which is very important for the practitioners, is how much of chopping should we do? Do you do only one top layer output class layer chopping, or do you think we can chop 4 more layers and start from a previous layer? Let's say, for example, you have finished, say, max pool layer at this block 4 pool, and you want to start from there itself. You want to do your own, say, 2-3 layers you want to add as collection of conv and max pool with ReLU. It's up to you. But the idea is transfer learning hyperparameter tuning is about what number of layers in a pre-trained model you want to retain, and how many of the pre-trained, how many new layers you want to add is the hyperparameter you choose, depending upon how much of the data which you're working on is close enough to the existing, what we call as data which is being used for training. So we run this as fitting. We find that this works very well, up to 98.5% for MNIST data, it's working. So we find that this is reasonably suitable architecture for our domain. So this is what I wanted to cover from a transfer learning perspective. But what you can experiment will be working with different image sets. For example, in the class, I've given you some icon classification. For that, if you want to add your own 2-3 layers on top of VGG, you can do that. In place of VGG 16, you want to do other, like Inception V3, you will want to load. So there are different pre-trained models, all of them available as out-of-the-box libraries in Keras, and you can run that. But see the beauty of this program. Your basic program is not more than 4 layers. It's about take basic loading of the data from the original pre-trained model. Then to that, you add these 2 or 3 layers which you want to custom add. Depending upon how much of reuse you want to do or how many layers you want to chop, you can go ahead and work with that many layers as you would want in terms of reuse of the knowledge already extracted from the training over the ImageNet data. So all in all, transfer learning is a very powerful technique. And we want to mention that we have to pay our respect to the people who have done the hard work of developing this architecture and made it ready for us, so that we don't have to do the hard work of training large networks, consuming huge amounts of memory and huge amounts of time for all types of custom problems. So going forward, unless otherwise specified, if your problem is very small, it's not a bad idea to go ahead and use transfer learning as a model for image classification rather than creating your own custom network.